we first need to show like okay, for it can be extended the similar what the definition is we extend it through the first row, right? So what we need to show is that if you expand it through like other rows, any other row, it will be the same as if you expand it through the first row. Of course, like we need to prove by induction. So first we prove, I mean, as a starting point, like we need to show like base cases, right? And base cases, obviously, we have to start from like the 2 rows, in order 2 by 2, right? So we know like A, B, C, D. I mean, the determinant of this is A, D minus B, C, right? So if you, we already see that if you expand through the first row, it's going to be this. And if we expand it through the second row, it's going to be C times determinant of B. And oh, by the way, like we have to like -1 plus 2, okay, and the plus, okay, -1. The second one is 2 plus 2, okay, and D times determinant of A. So you can see that this one is the same as this one. Okay, so you know the base case is satisfied. Okay, and so assume the induction hypothesis. Determine of A can be obtained by expanding through any row. Okay. So N is lower than here. So now, we want to consider determinant of A, which is column K row. And then arbitrarily pick A, I, E, A, I, I2, A, I, K, right? This is ice row, right? This is ice row. Okay. So it's going to be, if you expand it through this, we first know that according to the definition, this is going to be A11 minus C11 plus A12 plus C12 plus plus A one K, C1K, right? This is according to the definition. We expand through the first row, right? Okay. And we want to show that A I1 C I1 plus A I2 I2 plus plus A I K C I K is the same as the top one. We want to establish this. Is that right? So what are the relationships? Let's look at C11 and CI1. C11 is like, let's forget about like this -1 to the power something. Then let's look at the determinant of that matrix first. This one is you get rid of this and this, right? A11, I mean it's this matrix, right? Right? Okay, and this one is you get rid of this one and this one. Right? So let me find like a good proof and send to you like mine. Okay. But I think that it's more complicated than I originally anticipated. To be honest with you, okay. During the break, I tried to look up at textbook. I mean, actually, 2 to 3 textbooks. No textbooks talk about this. One textbook even say like, this is complicated, so we just skip it. You know, for but this should be proved. Okay, and I will show you the proof later on. I will send you the proof. Okay, in email. Okay, so that's because we really have to. If we stop here, too much time is not good. So let's assume, okay, we prove this. Okay, I'm sorry. Okay, so the determinant can be expanded. Okay, let's assume the determinant, we already proved determinant can be expanded through any row or any column. Okay, then there will be a lot of issues. Okay, let A be a square matrix, then determine A equal to 0. If A has an entire row with all 0 entries. Okay, so it's easy, right? It's a consequence. It's a direct consequence of the previous theorem because, like, we just expand your matrix. I mean, you just expand. Through that row, okay, that with all zeros, and then all the terms of your determinant calculation become 0. So, obviously, like the determinant of that square matrix will be 0. Okay, so that the first A is like a given. The second one is more interesting. If A has 2 identical rows or columns, by the way, for the first point, if A has the column with all 0, one column with all 0, I mean, the determinant of A is 0 too, because we know that we can extend through any row or through any column. So if there is a column that has all 0, then you can expand through that column to get a determinant of A is 0. Okay, as well. So the second one, okay, if A has 2 identical rows or 2 identical columns, then the determinant of A is 0 too. Okay, so this one can be done by induction. This is induction function. Say, in order for two, again, like starting as a base case, it has to start with 2 because like you have to have at least 2 rows to have something identical, right? So if you say you have like A.可以帮我们拿一下，另外一些，这2次都有。还有，写的没有关系。好 ，OK， that's A B A。Right? Then it's going to be AB minus AB, right? Regardless the value of A and the D, right? Okay, that's base case. So if like if this property holds for n smaller than k, okay, the induction hypothesis. Okay, for n smaller than k, like a determinant of A, okay, is 0 if okay, 2 rows or 2 columns. There you go. Okay. Then the induction set. Okay. How about determinant A, which is K times K. Then it's going to be we all know some generality. Let's assume these two rows are the same, okay? Let's assume those two rows are the same, okay? I mean, so you expand through like another row. Say this is you expand through this row. So it's AI1, AI2. Okay? So it's going to be AI1, CI1, plus AI2, CI2, plus AIK, CIK, right? For each C, okay, look at here. So for example, AI1, you get rid of this one, you get rid of this one. So you are calculating like this is like 1, I plus 1 is determinant of AI1, right? But because determinant of AI1, you can see there are two rows that are identical, right? According to our induction hypothesis, because now it's this one, to get rid of one row, one column, so the size of the matrix becomes like less than K, right? Less than K. So, and we have two identical rows. So obviously, this one is 0, right? This one is 0. Right? So for the same argument, all these are 0. So as a result, your determinant of induction system, that thing will be 0. Okay. I mean, for the column, if you have two identical columns, same thing, you spend through like a different column, and it's going to end up like for every the cofactor, it's going to be the same. Every cofactor will be 0. So the resulting determinant will also be 0. So this one is okay. Any question? Okay. And then, okay, if A is an n by n triangular matrix, then determinant of A is going to be like a multiple of the diagonal, like element. This one is also very interesting. Okay, so again, okay, because you are talking about triangle, right? So they are upper triangle or lower triangle, right? So, again, without loss of generality, we can assume that it's upper triangle. Okay? I mean, if it's lower triangle, I mean, it's similar, but it's just like you just need to do it slightly different. So it's if it's upper triangular. So basically we have like a value here. And all the other values here are there, right? So determinant of this. So you expand through the first row, first column. First column. So this is A11, right? So it's going to be A11 times C11, right? And then, okay, because A1, A21, A31, N1 are all 0. So all the other terms are gone. All the other terms are gone, right? And then you look at C11. C11 is going to be negative 1 to the power of 1 plus 1, times what? Times, so let's look at here. I mean, here, it's once again an upper triangle, right? It's once again an upper triangle matrix, right? A determinant of upper triangle matrix. So you can repeat the process, okay, and you get like this. From here you get like A22, and keep doing that. You get A11 times A22 times A22. Okay, this is one way to do it. Another way to do it is by induction again. Okay, because if it's like an upper triangular, if it's a 1 by 1, so it's A11 obviously. Okay, and if it's like if the size is lower than K, size n is lower than K, it's like that. So if it's greater than K, suppose it's upper triangular, then basically you just need to show, okay, extend to here. So it's this one times this one, but this one, you can directly apply the induction hypothesis to get like C22 times C32, blah, 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 blah. Yeah. Okay. So basically, like, this works for upper triangular. This also works for lower triangular, but it's just for lower triangular, you need to expand through like the first row. Okay. In order to make use of as many zeros as possible when you try to expand to get your determinant. How about this one? If A is a square matrix, we have like a determinant of AT equal to determinant of A. The transpose. Maybe I'll just take this one to you because I have shown you like several inductions. I mean, if it's 1 by 1, the transpose is equal to itself, right? So it's easy. In base case, it's easy, 1 by 1. Okay. But if it's lower than K, assume that it is the case. Like when it is the size is K, then you basically you try to follow like the proof, the definition, like try to expand, maybe through the first row, and then you have to show like it's the same thing as like you do a transpose. Okay. Because transpose like primarily is like you expand through the first row. The transpose you try to expand through the first column, because the first row is going to be equivalent to the first column, right? So here, the only thing I will just give you, the only hint I will give you is that you try to expand through the same thing. It's just like the original, it is a first row. Then after transpose, it becomes the first column, right? So on the left hand side, okay, so on the right hand side, then you try to expand through the first row. On the left hand side, determinant AT, you try to expand through the first column. That's it. And then you can easily show that they are identical. Okay, through induction. And there's an interesting theory. Okay, that A be an n by n matrix. We have AI1 times CJ1. This is very interesting. Okay, this I1 J1. Okay, I mean I and J may be the same, may not be the same. Okay, plus AI2 CJ2 plus A.